Hi everyone, in this lecture we are going to discuss another example problem for equilibrium of a two-dimensional rigid body system. Okay, and in these problems we have a beam that is simply supported, and when I say simply supported, the beams are supported using a pin and a roller or rocker. Okay, so the objective of this problem is to find the reactions of the supports. Okay, and then let's identify what type of support that is being used in this beam. Okay, so point B in here is a pin support, right? And point A is a rocker, right? Point A is a rocker. Okay, or you can call it roller. All right, so similar to other problems, the first step that we take to solve engineering problems most of the time is to draw the free body diagram. Okay, so let's start drawing the free body diagram. This is the beam. Okay, this is A, this is B. Okay, since it is a pin support, then I will put two reaction forces, By and Bx. Okay, and then since at A is a rocker, then I will have one reaction forces. Okay, and let's call that reaction forces is A. Okay, and if this is the inclined surface, right, in here, then this reaction forces is perpendicular to that inclined surface. Okay, and note that in here I use a dash, okay, in the arrow of the reaction forces to indicate that those are the unknowns that we are going to calculate. Okay, so this free body diagram is not complete yet. We are still missing the distributed force, which is triangularly distributed, right, and is acting on the top of the beam. All right, and in here the slope is 3, 4, 5. Okay, if you could recall what we have learned in module 2. Okay, then I will have in here, this is 3, 4, 5. Okay, so this 3 vertical one becomes horizontal in the fourth. Okay, my questions to you is why? Okay, right, so please try to think how can we write this triangle in here where 3 is right now the horizontal line. Okay, and then in these problems, okay, we need to find Bx, By, and A. Okay, and it seems like this is a general equilibrium case. Okay, so we can write 3 equilibrium equations, which is sum of the forces in the x equal to 0, sum of the forces in the y equal to 0, and sum of the moment at any point equal to 0. Okay, 3 equations, 3 unknowns, then this problem should be solvable. Right, before that, there's something that we have to do before we can calculate the reaction forces, is that to simplify the distributed forces right here. Okay, so we have to simplify the distributed forces right there. Okay, and to simplify that distributed forces, there are several ways, right? I mean, it could lead to several possible results, right? And I think just in here we just limit it to 2, right? So the first one is when we calculate the area over here, we will obtain one resultant force located right there. Okay, and then if we calculate this area right there on the right side, we are going to obtain another resultant force that has a similar magnitude. Okay, right here. Okay, right, and in here the distance in here is 2/3 times 3 meter, right, and distance right here is 2/3 times 3 meter. Okay, so this is one possibility. The second possibility is to have the whole things in here as one resultant force in the middle of the triangle. So in here this is 3 meter, okay, and this is R. Okay, let's call this R1, RL, or an RR. Okay, so here is just one R. Okay, this is BY, this is BX, and this is A. Okay, so no matter which system that you choose, system 1 or system 2, you will obtain the same reaction forces. Okay, so in here I would like demonstrate the solutions when we pick option 2. Okay, right, so when we pick option 2, the R over here is going to be area of the triangle, right? So we will have 1/2 times 400 Newton meter times 6 meter. Okay, then we obtain in here is 1200 Newton. Okay, right, and the reasons why in here this is 3 meter, because we know that the resultant force has to be located passing through the centroid of the triangle, and in here the centroid of this triangle is located along this line, right? It's located along this line because the triangle is symmetric, okay, such that we know that the resultant force has to be located along that line. Okay, so let's calculate. Okay, and in here using system 2, okay, which is this systems right here. Okay, all right, and let me try to copy everything one more time. So R is 1200, we already calculate, right? So I'm going to erase the details and just write 1200. Okay, and then the distance to point A is 3 meter, and I hope you guys right now have figured out that this is 4, right? This is 3, this is 5. Okay, why, right? So let me discuss why. So this is the inclined surface, right? In the inclined surface, we know that this is 3, 4, 5. Okay, and let's say this angle right here is theta, then the angle right here is theta. So right now my resultant force is going that way, right, perpendicular to the surface. Which is A. Okay, and then we know that if this angle is theta right here, right, then this angle here is also theta, right, and then the angle here is also theta. Okay, since that angle is theta, right, then we can redraw this triangle, we can rotate this triangle, right, rotate it 90 degrees, right, then we will have this triangle right here, right? So this is 3, 4, 5. Okay, where this angle right here is theta. Okay, I hope it's clear now. Okay, with that, we also know that the distance right here is 6 meters. So let's write the equilibrium equations. I will start with sum of the moment at A. Okay, the reason I start with sum of moment at A, because from experience I already know that when I take sum of moment at A, only By and R that has contribution to sum of moment at A. Okay, since we already know R, right, then we can calculate By right away. Okay, so let me write sum of moment at A is By times 6 meter. Okay, and with respect to point A, By is going upward, then it will have a counterclockwise, right, a counterclockwise rotation. So in here it will have a positive sign. Okay, then for R, the distance is 3 meter, right? The perpendicular distance is 3 meter. This is this distance right here. Okay, so R times 3 meter, then equal to 0. And with respect to point A, it will have a negative sign because it will have a clockwise rotations. Okay, so it will have a clockwise rotation with respect to point A. Okay, about point A. So now we have this, we can solve By directly. So By is R times 3 divided by 6. Okay, so I move this to the right hand side equations and then divided it to 6. Okay, then here I will obtain that By is equal to 600 Newton. Alright, before I write the next equations, I think some of you may ask questions. Why is that Bx and A does not contribute to sum of moment at A, right? So the reason Bx does not contribute to the sum of moment at A, because if you extend the line of actions of Bx, it passed through A, right? It passed through point A. So there's no moment arm. That's why there's no contribution of Bx to sum of moment at A. Okay, and then the reason why A, the force A, does not have contribution to the sum of moment at A, because the force A is passed through point A, right? So there is no moment arm and there's no contribution to the sum of the moment at A. Right? Only By and R that has a moment arm. Okay, when we take the moment about point A. Then let's write the second equation, which is sum of the forces in the Y. Okay, then in here we have By, right, which is the force in the Y directions at B, and R is going down, so it has a negative sign. Okay, and then the Y component of A, right, the Y component of A is going up, right, based on our assumption in here. Then AY times 4 over 5. Okay, remember that in here this is A, right, this is the Y component of A, right, and this is the X component of A, and this triangle right here is proportional to this triangle right there, 3, 4, 5. Okay, so you can calculate AY by taking this component, okay, divided by this component over there times A, right? And AY is going up, so we have a positive sign right there. Okay, and it's equal to 0. Okay, all right, since we already calculate By before, then in here we can calculate AY, right? So we know By is 600, this is 1200, so we can calculate AY is R minus By, right, times 5 over 4. Okay, So in here we will obtain ay is equals to, oh, I think I make a mistake. So this should be a, no longer ay, okay, because this whole thing is ay, okay, this whole thing is ay, okay. So when we calculate this should be a, so we will obtain in here is 750 Newton, okay, right? So I repeat again that the sum of forces in the y consists of by positive because the force we assume is going up, okay, and then r is negative because it's going down, okay, and the y component of a is positive because we assume it's going up, okay, and it's 4/5 divided times a, okay. So based on these equations we can calculate a as follow. We obtain 750 Newton, okay. The last equations that we can write is sum of forces in the x direction, okay, and in here the first force is bx, right, and then the second force is ax, okay, and we assume that ax is going to the right there, okay, we assume it's going to the right, so it's positive, and set it equal to 0, okay. So in here we have bx and ax is 3, right, over 5, right, 3/5 times a is equal to 0, okay. So we have known what is a, right, then in here we will obtain that bx is negative 3/5 times 750 Newton, then we will obtain negative 450 Newton, okay. So the negative sign means that it will go to the directions opposite to the one that we assume initially, right? So let's finalize, and I like to resketch everything one more time in here. This is our beam, right? This is the distributed force, okay. This is a is 750 Newton, okay. This is by is 600 Newton, and bx is going to the other directions is 450 Newton, okay, and the intensity of the distributed force in here is 400 Newton per meter. All right, let me review it again in here. So in here we start by identifying the support and what are the reactions forces corresponding to that supports, right, and then we simplified the distributed forces, right, to calculate the resultant and its location from certain point at a beam, okay. So there are two options. Option 1, where you have two resultant force RL and RR based on the left side triangle and the right side triangle, okay, and then the second option is to calculate the resultant force based on the entire triangle, okay, that is symmetric at the midspan of the beam, okay. So we can calculate the resultant as the area of the triangle, and it's located at the midspan because we know that that triangle is symmetric about the midspan, okay. Afterwards we write the equilibrium equations, right, to solve for the reaction supports bx, by, and a, okay. And I think that's it for this lectures, and thank you for listening.